Okay, so finally let's start putting this all together and see if we can predict whether something's going to go SN1 versus SN2. So we'll use a lot of the things we just went through. So the first step before getting into this video is one, learn the mechanism for SN1 and learn the mechanism for SN2 so you can actually understand what the difference is, at least in terms of arrow pushing. And then two, understand what good nucleophiles are and bad nucleophiles are. So before you even bother with this, I would say one is know the SN1 and SN2 mechanisms. It's kind of a no-brainer, like you have to know the difference between them. Two, know at least what a bad nucleophile looks like. And then three, is there anything else? Three, I would try and understand the role of strong acid. This one's less important, but still you need to know it. Understand the role of strong acid in making bad leaving groups into good leaving groups. Okay, so that's where you're using something like a strong acid to convert an alcohol into or protonate it so that it becomes water when it leaves instead of hydroxide. Okay, so but definitely know this. And then also I feel like, man, this is going to be such a struggle if you don't know this. And then it doesn't hurt to know this last one. So this is like the least important. Okay, all right, so remember, this is something you also should probably know, but remember that for SN2, it's favored, and this is really the rule, right? Like, so we can talk about the trends from tertiary to secondary to primary, but really it's favored by not having steric hindrance. In the approach to the back side of the electrophile. So that means that I'm just going to use, let's just say the leaving group is iodide. Sorry, another confusing thing is that good leaving groups also make good nucleophiles. But there's not much we can do about that. It's just the way Mother Nature worked out to make everything really goddamn confusing. If you want to have any kind of realization around that, read a book on quantum mechanics, and then you'll be like, this makes no sense. Anyway, all right. But yeah, so SN2 is favored by not having steric hindrance in the approach to the backside of the electrophile. So remember, our backside is here, and so you don't want a lot of steric hindrance there. But also, when your nucleophile is coming in, you don't want a lot of steric hindrance on your nucleophile. So let's say you're this nucleophile, okay? Ammonia, pretty small, not a lot of steric hindrance. But if we were to use, say, trimethylamine, now our nucleophile has become sterically hindered, right? So we want a small, not sterically hindered nucleophile. Okay, that favors SN2, and then we want a not sterically, not sterically hindered electrophile. So these are kind of our two rules here. We don't want the nucleophile to be sterically hindered. And as we discussed in previous talk, we definitely don't want the electrophile to be sterically hindered. Okay? Both of those things disfavor SN2. I'm sorry, both of these things favor SN2. So you want it small and not sterically hindered. You want to get rid of sterics altogether. And then you want the nucleophile to be good or moderate. So bad nucleophiles generally don't go through SN2. We can talk about why that is. Okay, good or moderate nucleophile. I should finish that thought. There we go. Okay, so those are kind of our three things. All of these things come together to favor SN2. And so that's what's going to favor SN2. And if we want to put that into some, for nucleophiles, it's a little bit harder to do. You just kind of have to accept that you have to make the judgment call on how small or not sterically hindered the nucleophile is. And I'll talk about what some examples are where they're not, where they are very sterically hindered. But in terms of the electrophile, we know that a primary is going to be better than a secondary. It's going to be better than a tertiary. Actually, let me draw that out differently. So we can say, we'll even say methyl. Primary, secondary, tertiary. So these favor SN2 going in that direction, right? This is when we're talking about the electrophile. So try and stick with the same colors here. So if we're looking at the electrophile, this is sort of our situation. Yeah, small, not steric. So this is for the small, not sterically hindered nucleophile. What do we mean by that? So most nucleophiles are fine for doing SN2. As long as it's a good nucleophile or moderate nucleophile, it can do SN2. If we want to not have it do SN2, which is sometimes the case, you use things that are sterically bulky. So for example, trimethylamine probably would not make a good nucleophile. And if we were to compare this to, say, dimethylamine, okay, now we're looking at something that's a better nucleophile. All of these could reasonably do SN2, but it becomes less and less favorable as you go, at least in this case, from left to right. Let's see. And I'm just choosing amines because, you know, it's just an example. There's lots of different nucleophiles. But these would favor SN2 this way. I'm not sure if that helps. I mean, it just looks kind of scribbly. Trying to, you know, take advantage. Jesus, take advantage of the color coding to kind of make things a little bit clearer, but it's hard. I'm just not super used to the iPad yet. That looks a little better. Okay. And then good or moderate nucleophile, you'll have to go back and look at your nucleophile list for that. But like, let's look at some. So this is here we're talking about the nucleophile. We can look at some other nucleophiles.